Next topic is path cycles and connectivity. So in a graph, what do you mean by a path? So basically, starting at a vertex in a graph, we are using the edges available at that vertex to move to other vertices and travel through the other vertices to reach an end vertex. Right? So such a traversal or traveling is called a path. Okay. So it's basically we can represent it by which vertices and which edges are being chosen as a sequence. So suppose we are starting at V1 using there are two edges available at V1. Using the edge E1 I am going to V2. So V1, E1, V2 represents that travel. Now V2 I am having two edges E2 and E6. I'm using E2 to, if you use E2 you will be reaching V3. So E2 is used, you are reaching V3. So once an edge is used and vertex will be following it. Okay. So after a vertex you will use an edge and at the end of that edge you will be having another vertex. So it is an alternate sequence of vertices and edges you are having having here, right, for representing this travel. You are starting at V1 using the edge E1, you go to V2 using the edge E3, you go to V3, right? So that is already given, that sequence is already having, we have here. Now from V3 you are using the edge E5, which is this edge, to go back to V1. We will be reaching V1 with E5. Now from V1 you use E1 again to go to V2. So this is the corresponding travel we are conducting. V1 to V2, then to V3, then to V1, then to V2 again using those edges. So that sequence is called, this sequence of vertices and edges represents exactly that traveling. So it is called a path. So it's a sequence of vertices and edges, alternate sequence, where each edge is coming between corresponding end vertices of it. Okay. So if you don't repeat any edges in a path, you will call it a simple path. Okay. So this path is not simple because you have repeated the edge. This edge we have repeated E1, right? In the sequence we have E1 is repeated, therefore in this traversal energy is repeated, so that path is not simple path. Now you consider this path V1 to V4. Okay, V1 to V4, V1 to V4 using E4, then to V2 using E6, then to V3 using E2, V3 using E2, then to V5 using E7. So this particular travel or this particular path, what about it? Then none of the edges are repeated here, so it's a simple path. Okay. A number of edges in a path, whether it is simple or general path, this number of edges we'll call it the length of the path. Okay. For the first path, which is not simple path, you have E1, E2, E5, E1 are the edges used. So four edges are present in the path. E1 is repeated. You are not considering how many distinct edges are there. You are finding how many edges are being used. 4 edges are being used in this path. So the length of this path it is 4. Length of the second path it is 1, 2, 3, 4. That again it is 4. Now what do you mean by cycle or circuit? So cycle or circuit as analogous terms here we are using. So if the initial and final vertex of a path, the initial and final vertices are same. You are starting at a vertex say V1, you are ending at V1 itself in a path. In that case you can call it a cycle at V1, right? Cycle or circuit at that particular vertex. That is, if the initial and final vertices of a path are same, then you will say it's a cycle or circuit. Now if it is a simple path for which you are having initial and final vertices are the same, then the path is called a simple cycle or simple circuit. Okay. So Yeah. So that's the idea of a simple cycle or simple circuit. So actually you can repeat the vertices in this case, right? So the simple path, simple cycle, if you take, since it's only required to be a simple path, it can repeat the vertices basically. So I can have a cycle starting at this, in this graph. Is it possible? V1, this V22. Okay. Check that, is it possible? So I can start at this vertex, go to this V4, then to V5, V3 to V4, V4 to V5, V5 to V3, V3 to V1, V1 to V2, V2 to V3. So with this definition, this is also a simple cycle, but in general actually vertices cannot be repeated other than the initial and final vertices for a simple cycle, but here we are using it in this sense, the definition we are using in this sense. So it only requires to be a simple path with initial and final vertices are the same. So simple path is a path in which edges are not repeated. Now such a path, the initial and final vertices are the same, then you'll say it is a simple cycle or simple path, provided it is not a loop. You should be having non-zero length. Yeah, if it is a loop also, you have the length is 1 there, right, for that path. So yeah, non-zero length means it's not a single vertex, and we are not at a vertex itself, we are moving. So in that case, so it's just a non-trivial case you are having. You are not having this path as a single vertex only, right? There is at least one edge, either a loop or other non-loop edges are there, then you'll be having non-zero length. Okay, so that is the idea of a cycle. Now you can define the connectedness in a graph. If every pair of distinct vertices you choose in a graph, you can find path from one vertex to the other, in that case you'll say the graph is connected. So from every vertex, each vertex in the graph you choose, from that every other vertices are reachable through paths in the graph, then the graph is called connected. So in this particular graph, any pair of vertices you choose, there is a path between them, so this graph is connected. But this particular graph, if you choose, between the vertices ABC, you have paths are existing. Between the vertices of DEF, you are having paths are existing. But if you choose a vertex from here, say D, and a vertex from here, which is A, there is no path starting at D and ending at A, or starting at A and ending at D. There is no path, right? Therefore, we say A is not reachable from D in this graph. So there is no path, basically there is no path from D to A in this graph. Therefore there exist vertices which are not reachable from a vertex in this graph. Therefore the graph is disconnected. Now you check what are the maximally connected parts. So for this graph ABC, this part of the graph, it is maximally connected. If you only choose AB, I can also include C and make it a bigger connected part of the graph. The maximal in this sense, if you add any more vertices from the graph with the corresponding edges available at it, the graph is not connected. So in that sense, ABC, this part is a maximally connected part. In the same sense, this is also a maximally connected part. You have exactly two maximally connected parts for this graph. So such maximally connected parts, you'll call they are components. So you have two components here. For the graph G2, there are two components. This is the first component, this is the other component. Okay, so components are basically connected parts of the graph which are maximally connected. Okay, now there are few results. So this result without proof we can take as a statement. If the graph is connected or disconnected, doesn't matter. If you have two vertices, exactly two vertices which have 4 degree, then connecting these two vertices you have a path always. Okay, so that is the first result. The next result with proof you should be knowing. If you take any graph, right, it's a simple graph with n vertices. In that case, the upper bound for number of edges, it's a simple graph. The maximum number of edges possible for a graph is when it is complete. So if it is only given that n vertices are there in the graph, the maximum number of edges possible will be in the case of the corresponding complete graph, which is nc2 or n into n minus 1 by 2. But if we are having it's a disconnected graph with k components, then we can find a much better bound for the maximum number of edges in the graph, right? So you have a simple graph with n vertices and k components, then it will have can have at most this many edges, n minus k into n minus k plus 1 by 2 edges. So how do you prove it? You are given that it's a disconnected graph. So its components are k number of components are there. So you consider the components be g1, g2, etc. gk are those maximally connected subparts, right? So maximally connected parts are g1 to gk. So consider you have n1 number of vertices in the first component, n2 in the second component, so on, and k in the kth component. So if you sum the number of vertices in the components, you will be getting how many vertices are there in the graph. So for this particular graph, it is 3 in this component, 3 in this component. The sum is 6, which is the total number of vertices in the graph. So if you sum n1 to nk, you will be getting what is the total number of the vertices in the graph. That is already given to you as n. So n1 plus n2 plus etc. nk is n, right? Now the component gi, for that ni is the number of vertices. For I equal to 1 to k, g1, g2, etc. gk has n1, n2, etc. nk number of vertices. In gi, how many edges will be there maximum? Right, maximum number of edges, it is ni into ni minus 1 by 2. So you can write edge set of gi contains less than or equal to this number, ni into ni minus 1 by 2 of edges. Right, yeah, that's already here. Okay, so this you can write because it is the maximum edges possible there. Now edge set of G will contain how many edges, right? How many edges will be there in the edge set of G, or how many edges will be there in the graph G? That is the number of elements in the edge set of G, which will be sum the number of edges in each components. The number of edges in the graph is number of edges, sum of number of edges in each of the components, right? So you have k components g1, g2, etc. gk here. Sum the number of edges in each of them. You'll be getting what is the number of edges in G. Now number of edges in gi, it is bounded by this, so that you can write number of edges in G, it is less than or equal to summation I equal to 1 to k of the number of edges in each gi, which is this one, right? Now what is the maximum possible value for each ni? You have ni is maximum if all the remaining, so ni is the number of vertices in the ith component. If all the remaining components are having minimum number of vertices, in that case ith component will be having maximum number of vertices. So what is the minimum number of vertices in any component? It should be 1 at least, right? Otherwise that component is not there. So consider for G1 what will be the maximum number of vertices you can have. It is happening when G2 to Gk, other than G1, all the other components are having exactly one vertex, the minimum number of vertices possible. In that case G1 will be having maximum number of vertices. So what is that number? Total number of vertices is n. So k minus 1 remaining components other than G1 has exactly one vertex. Therefore already k minus 1 vertices are chosen. So remaining vertices are n minus of k minus 1 or n minus k plus 1. That many vertices is the maximum possible vertices in G1. Similarly for any I. So Gi, the maximum number of vertices possible will be, from n you have to subtract the sum of minimum number of vertices possible in all the remaining components, which is k minus 1. So n minus of k minus 1 or n minus k plus 1 is the maximum number of vertices possible in the component Gi. So this is a constant, n is a constant, k is a constant, ni is varying, right, depending on the component you are having. So in the summation we got here, you can replace ni with this bound. So ni is less than or equal to n minus k plus 1. If I replace, I'll be getting number of edges in G is less than or equal to summation I equal to 1 to k n minus k plus 1. That is what you have replaced for ni. The remaining part is ni minus 1 by 2. Now that constant out of the summation you can take outside, because in the summation I is varying. So in n minus k plus 1 there is no I involved, index I is not involved, so I can take it outside. By 2 also I am taking outside. What remains, summation I equal to 1 to k ni minus 1. So the summation is n1 plus n2 plus etc plus nk, which is your n minus 1 etc k times, so minus k. So summation ni minus k is what you are going to get. What is summation ni? It is n. So you'll be having this is n minus k. So n minus k plus 1 by 2 into n minus k. So number of edges in G, it is less than or equal to n minus k into n minus k plus 1 by 2, where n is the number of vertices and k is the number of components. Okay, so this result we can prove in any simple graph. Okay.